Okay, this is 11-1, which is about identifying 3D solids and also looking at cross sections of these solids. Let's start off talking about polyhedrons. You remember that a polygon is a figure made up of straight line segments. There are no curves in polygons. Well, similarly, there's no curves in polyhedrons. These are 3D figures bounded by polygons. So there's a couple different groups we're going to be looking at. We're going to be looking at prisms and pyramids. There are other polyhedrons besides these, but we're going to focus mostly on prisms and pyramids. So what is a prism? It's a 3D figure. Um, Basically, it has two bases that are both parallel and congruent. So this you could call this a square prism or a rectangular prism. Its bases are on the top and bottom, but you could also look at the bases as the front and the back, or the left and the right. It just depends on your perspective. This figure, however, would be nothing more than a triangular prism. You can only look at it one way. The bases have to be parallel and congruent to each other, and you name the prism according to its bases. Now, if the figure has one base and rises up to a point, we call that a pyramid. This would be a square pyramid. This one would be a triangular pyramid because its base is a triangle. Pyramids are pointy, basically. They have a base and a point. But there's all kinds of other polyhedrons. I could make a cube, which is a prism, and then put a pyramid on top of it, creating a whole new polyhedron that you couldn't call a prism or a pyramid. It's a combination of the two. It's sort of a composite figure. And then, this other figure and this one, these are just other polyhedrons. Now, non-polyhedrons would be, for us, the figures that have curves. So cylinders, cones, and spheres we're going to be looking at. Cylinders are much like prisms. They have two bases. They may be oblique, which doesn't change the volume of them, but it does change the surface area. Um, Cones are sort of like pyramids. They're pyramids with circular bases. And then spheres, of course, you know where the sphere is. The Earth is a sphere, a beach ball. You get the idea. Okay, now you try identifying this polyhedron. Well, it's got one base. The top is pointy. All the edges rise up to meet the point at the top. So I definitely think this is some kind of pyramid. What kind of a base does it have? It's got, looks like a pentagonal base. So this would be a pentagonal pyramid. Try this one. Now, you might always think of the base as being on the bottom, and you might want to call this a rectangular prism because the base is on the bottom, and the top has also got a rectangle. But that rectangle, although parallel to the bottom, is not the same size. So this could not be called a rectangular prism because the bases have to be both parallel and congruent to each other. If you look at it a different way, the front and the back are parallel and congruent, and those are trapezoids. So this is called a trapezoidal prism. How about this one? It's not pointy, but it does have parallel and congruent bases, which are both triangles, so this would be a triangular prism. This one's pointy, has one base, and the edges rise up to meet this point on the right side, so this would be a hexagonal pyramid. Alright, so this figure here would be a square pyramid. We're going to name some elements of this pyramid, the vertices, the edges, and the faces. So the vertices are basically the corners, the vertexes, where the line segments meet. So point A, that's a vertex, B is a vertex, points C, D, and E, those are all the vertices. It's got 5 vertices. The edges are the line segments that connect all these points. So segment AB, that's an edge, BC is an edge, CD, DA. There's 4 on the bottom, and it looks like there's 4 lateral edges. Those are side edges. So it's got a total of 8 edges. Now the faces are the sides of the figure. So this bottom face is a square, that's square ABCD. And the one on the left here, that would be a triangle, triangle ADE. There's a triangle in the back, triangle ABE, and a triangle on the right side, triangle BCE, and then there's one in the front. So as far as faces go, there were 5 faces, a square and 4 triangles. Okay, so Euler lived about 300 years ago, and he discovered this about polyhedrons. If you add 2 to the number of edges, it equals the number of faces plus the number of vertices. Formula is real easy to remember because I put it for you in alphabetical order here. So 2 plus E equals F plus V. E is the number of edges. Let's count the number of edges on this rectangular prism. You've got 4 on the left, you've got 4 in the middle, 4 on the right. That's a total of 12 edges. Number of faces is pretty easy to count. You've got 2 bases on the left and right, and you've got 4 lateral rectangles making up the sides, top, bottom, front, back. So that's 6 faces. And then you've got number of vertices. You've got 4 on the left and 4 on the right. So if we plug this into his formula, we see that it's true. And it's going to be true for all polyhedrons. Let's check it for the figure here, which is called what? It's called a hexagonal prism. So number of edges, we've got 6 on the left for the hexagon, 6 in the middle, 6 on the right. That's a total of 18 edges. Number of faces, let's see, we got 2 bases and 6 lateral rectangles, so that's a total of 8. And then the number of vertices, you got 6 on the left and 6 on the right. That's a total of 12. We plug it into his formula, it checks out. What will this look like on the quiz or a test? I'll probably give you 2 of the unknowns and ask for the third. Okay, you may remember this last problem, or this problem from, I think it was 2 chapters ago when we were doing Pythagorean theorem. And the way you did it was you had to find first the sides of this right triangle. The base is unknown there, but you could put up another right triangle and first find y using Pythagorean theorem. That's a 6, 8, 10 triangle. And then use that to find x. That's how we did it initially. And then I can't remember if I showed you another way you could do it using this formula. It's basically, it just gets you right to the answer. You don't have to do 2 right triangles. You could just use this distance formula. It's the square root of the leg squared plus the width squared plus the height squared. And it gets you the same answer. So you could do this either way. The formula is what I want to draw your attention to, though, because we're going to be using that in this chapter. So let's just practice using the formula once with this one. This will not be in the homework, but it is on the quiz, and I think it's on the test as well. So we need to do this at least a few times. You just plug the numbers into the formula and let your calculator do the work, basically. It's the square root of 230, which you could estimate if you wanted to. Okay, so we're looking at coordinates now in 3D space. We no longer have just 2 axes. You can see what was the x-axis is now the y-axis, and what was the y-axis is now the z-axis. The x-axis comes out of the screen at you, so you have to kind of imagine this in 3D space. It's kind of hard to draw on a flat piece of paper, I know, but or on a flat screen, but we're just going to do our best to visualize it. So the first point here, x-coordinate of -2 means I go back 2 units. Y-coordinate of -3, I go left 3 units, and then z up 4 units. So that would be my first point. My second point, 4, 5, -2, I go forward, or out at the screen 4 units, right 5, and down 2. And now I'm supposed to try to find the distance between those 2 points in 3D space. So you might be asking, how the heck are we going to do this? Well, we're going to use our distance formula. I'm going to modify the distance formula a little bit so that we can use coordinates. But basically, you just plug the numbers in. You're subtracting the x-coordinate squared, the y-coordinate squared, and the z-coordinate squared. And you work it out. And it's no different than using the distance formula when you have just 2D space, except it's got 3 dimensions. Another thing you're going to be asked to do is find the midpoint of 2 points in 3D space. And that formula is very similar to the one you know already. You're going to average the x's, average the y's, and average the z's. So once again, you just got to remember your midpoint formula and adapt it for one more dimension. And if we plug the numbers in, we see that the midpoint of that green segment we saw before is 1, 1, 1. And I remind you that this is not in the homework, but it is on the quiz. And here's just a little bit of reminder what a net is. If you have a 3D solid and you wanted to open that up into a 2D net, it's sort of like you have a cardboard box manufacturer would have to deal a lot with these 2D nets because they're starting with a flat piece of cardboard and they have to morph it into this 3D box. So this is what they'd stamp out of the cardboard and they'd fold it up into the box. 2D net is just a 2D image of a 3D solid. If you get something more complicated, like say a cylinder, the lateral area rolls out into a rectangle, and then you've got the two bases, which are both circles. These, you've got a triangular prism, opens up to this. The cone's really weird. The bottom obviously is a circle, but this part is not a triangle. It's actually, I don't know what that is. And then this one consists of 4 triangles. Another challenging thing you might be asked to do is to see whether a net could fold up into a cube or not. So what I like to do is color in the bases, and then it's easier to see that yes, that would actually fold up into a cube. How about number 2? Well, if that's the base, where's the top? You know, it can't be there. So that's a big no. That's not going to fold up into a cube. How about number 3? Will that fold up into a cube? Let's see if I color that as the base. You can sort of visualize the sides folding up, and then this would be the other base. So yeah, that actually would fold up into a cube. How about number 4? If that's the base, where would the other base be on top? It would be this one. And this would actually fold up into a cube as well. This one? Yep, folds up into a cube, and this one also does. Okay, so the next thing we're going to be looking at are cross sections of polyhedrons. So it's when you take a plane and intersect it with the figure. So our first figure is not a polyhedron, it's a cone. But what would it look like if a plane crossed through this cone parallel to the base and through the vertex? What sort of figure would it form? Well, it's going to cut right through the top of it, right through the vertex. It's going to form a point. Now, what if the plane comes through and it's parallel to the base, but it doesn't go through the vertex? Well, then it's going to slice right through the middle of it. It's going to form a circular region. How about a pyramid? If we go perpendicular to the base through the vertex, it's going to form a triangle. How about perpendicular to the base but not through the vertex? You have 2 choices. It could go through like this, forming a trapezoid, or it could go through the corner of it, forming a triangle. I can't think of any other way. And then finally, let's look at this prism. If we slice it parallel to the base, obviously that's going to be a hexagon. If we slice it perpendicular to the base, what would that be? No matter how you slice it, if it's perpendicular to the base, you're going to get some sort of a rectangle. And I don't know, I may have told you this story. This is a question that was asked of me when I was taking a test to become a math teacher. How many different polygons can be formed by slicing a cube in 3D space? And I don't know if I told you the story, but I got really frustrated because I couldn't remember what a polygon was. And I just wrote a poem. I don't know if I told you that story or not, but yeah, you're not going to write a poem. You're going to tell me all the polygons. Obviously, you see one here. This is a rectangle. You could also have a triangle, a square. It's possible to have a pentagon, a hexagon. Notice with the hexagon, it cuts through all 6 faces, the top, the bottom, the left, and the right, and the front and the back. Would it be possible for you to make an octagon with this? No, because an octagon would require it to have 8 faces, and a hexagon doesn't have 8 faces. Okay, and here's your mistake of the day. If my plan proves successful, folks, we're just going to continue as we have been. I'm going to make videos on YouTube for you so that you can get your lessons. You won't have to read the book so much. And I'll also be posting answers to the homework with all my work showing how to do the problems. We'll still have weekly quizzes on Illuminate and tests also on Illuminate. And I'm going to continue doing the Math Power. You can send me your responses to the Math Power through email. All right, well, that's all for today. Thanks, and I'll talk to you soon.